Hello everybody, and welcome to a very special edition of our AP Physics 2 seminar. Today we're continuing our study of modern physics, and we're going to take a little stroll down memory lane and look at the sort of history of atomic physics. So the goal of today, and yes, I am left-handed. You're going to take a while to see what I'm actually writing. Deal with it. We're going to take a little stroll down memory lane to sort of see all the improvements and breakthroughs that have been made in atomic study, going all the way back to ancient Greece, and finally working our way up to the beginning of the 20th century, where real breakthroughs were made in, figuring out what atoms were made of and all about. So let's start our journey. We're going to head, as I said, to ancient Greece. And we're going to meet some dude named Democritus. Now, Democritus was a philosopher, and based purely on philosophical notions, he was one of the first people to really come up with the idea that matter is made up of smaller bits. And so he called these bits atoms, or atomos, from the Greek word for indivisible. And he and his group of philosopher followers were known as the atomists. And I think Democritus and the Atomists would be a really killer band name if you're looking for such a thing, so keep that in mind. But, he was sort of the first idea of atoms. This is purely a philosophical argument. He had no evidence for this whatsoever. So what Democritus said was that, matter is fundamentally pure, but we know that matter decays. And so matter must decay into smaller, purer things, and we call those things atoms. So it's a purely philosophical argument based off notions of purity and how we know that matter can decay. But there was really no evidence for this argument. They didn't have the tools or the experimental capabilities of actually proving this thought. So an awful long gap happens between then and sort of the next breakthrough. In the 17 and 1900s, chemistry was sort of the science that was popular then, and chemists did a lot of theoretical and experimental work during this time. And one thing they were actually able to do is because they worked with atoms, how atoms build and connect with each other to make new kinds of molecules, they were able to figure out that the size of the atom had to be around 10 to the minus 10 meters. And that was a pretty accurate, that's not a word at all. Around 10 to the minus 10 meters. And, Swedish guy helped figure this out. Symbolized with an A with a little circle over it. We call this the angstrom. And this is a unit that is used in atomic physics to, roughly measure something about this size. And it's a pretty good measurement for all the what they knew during this time. This was a very good measurement. So later on, towards the end of the 1800s, new technologies began to be discovered. People were working with electricity, and we had this idea of cathode ray tubes. Essentially, a cathode ray tube would spit out electrons. So you could form a beam of electrons using this technology. And so what we figured was that matter had to be made of at least electrons for this to happen. We don't know what atoms were, but we figured this electrically charged particle coming out of a cathode ray tube had to be a part of all of this. So these electrons were discovered by a guy named J.J. Thomson. And based off his sort of favor of electrons, he learned a lot about them. So one, he figured it had to be smaller than atoms if they were being, coming out of them, and the atoms were still there. And he knew they were negatively charged. So he knew, like we found out in our first unit with electrostatics, that matter was neutral. So if the electrons, which seem to be part of the atom, were negatively charged, there had to be some positive bit to balance that out. And that positive part needed most of the mass. So he proposed a model. Here's our atom. It's a big old circle. And we have these tiny negatively charged bits in there, which he called the electron. And it's surrounded by this sort of goop. He called it jellium that was positively charged and surrounded that. So he got this model. It's called the plum pudding model, which says that the atom was a cloud or a jellious substance of positive matter with a bunch of electron bits floating in it. Basically, this model is backwards from what we know today. But it did solve the problem. He needed a larger amount of positive mass to make up for the fact that electrons were much, much smaller than the atoms themselves. So this was good enough for the time. It wasn't until around 1903 that we have a dude named Rutherford. He was from New Zealand. And he proposed a famous experiment to sort of reverse the plum pudding model and get us to what we now know today. So Rutherford, as you might know, is known for what is called the gold foil experiment. What he did was he had a piece of golden foil, and he would shoot essentially alpha particles, which are helium nuclei, at this gold foil. And so, because these are nuclei, he didn't know they were nuclei at the time. He was about to discover what a nucleus was, but he discovered that alpha particles could be produced in radioactive decay, and he was able to produce a beam of these particles, which he would launch at a sheet of gold foil. So if the plum pudding model was correct, we have this sort of large mass of positive charge. We're shooting these positively charged particles at this mass. And what would happen is as these particles enter, there would be slight deflection. Opposites attract, like charges repel. So this positive charge would be lightly deflected by just sort of this sea of positive charges interacting on it from all directions. So the path should be this sort of gentle deflection upwards if the plum pudding model was actually correct. So this is what was expected to happen if Thomson was right. What we actually saw happen was much, much different than they expected. So what we saw was that every once in a while, we would have these particles come in. Alpha particle would come in and bounce off very, very strongly. So instead of the gentle deflection that they expected, they saw these sort of complete ricochets of the alpha particles off of the gold foil in a completely opposite direction. And this can only happen if, the positive portion of the nucleus was, in fact, very compact. Sorry, not of the nucleus, of the atom. The positive portion of the atom was in fact very compact in the form of what we now call the nucleus. So Rutherford's experiment, it ousted the previous plum pudding model, now saying that, maybe we have it the other way around. Maybe we have this strong centralized positive part with a sea of electron jellium. So the jelly was in fact negatively charged with little positively charged plums instead. Rutherford's model was sort of the dominant model of the time. There were some mass issues. We would find that, if, hydrogen, based off its, having one proton, a charge of -1, its mass was 1. Helium, has a charge of 2, but then its mass was 4. And then lithium, going up the scale, on average, its mass would be 7 in atomic units. And so what people around this time figured out was that maybe the nucleus has a neutral part to it as well that can make up for this mass difference. So we have this mass difference. This was solved by suggesting there are neutrons. So not only did the neutrons solve the mass difference, they also kind of solved the problem of, if I have a helium, for example, I have 2 protons. We know that like charges want to repel from each other, and so these neutrons also provide glue to hold these positive charges together. And based off this idea, we now have this idea of a different idea of atomic mass number, symbolized as A for atomic mass, I guess. We have Z, which is the charge of the protons. And we're going to add to that the number of neutrons. So the total mass of the atom is the number of protons it has plus the number of neutrons it has. And they found that different atoms can have the same kinds of atoms can have different numbers of neutrons, giving way to isotopes. So isotopes are, atoms of same kind with different N values, different numbers of neutrons. So while the Rutherford model was great, it sort of solved all these problems. It fixed, it discovered that there's a centralized positive portion of the atom. It discovered subsequently that there had to be some neutral part as well to hold it all together. Rutherford did have some issues. From a classical standpoint, from what we knew about how charges moved, these atoms should not have been stable. If an electron sort of orbits around this center, it would necessarily have to accelerate by being in some form of circular motion, and that acceleration would cause the charge to radiate. And as it would radiate, it would lose energy and eventually crash into the nucleus, destroying matter as we know it. This obviously does not happen, and so that kind of suggests that there's something a little off with this model here. So the electron orbits around the nucleus, it should radiate and lose energy. So that's kind of a red flag there. In addition to that, that radiation should be a continuous spectrum. So we should see all the visible colors of light emitted in that radiation, but instead what we see are only a few colors or wavelengths in that spectrum. So that kind of suggests maybe there are only certain levels that the electrons can live in. If they're not just orbiting around willy-nilly, maybe they have to be fixed in certain positions. So we enter this dude named Niels Bohr. He was Danish. And he suggested that maybe they don't orbit around every which way. Maybe they're fixed at only certain levels. And that maybe these spectrums are caused, maybe I'll move that so you can see what I'm drawing. If I have two electrons here, maybe these energy levels, these discrete wavelengths I can see, are caused by moving electrons up to an excited state, which when it decays down emits that specific color that we see. So this here would be an excited state because I have an electron hopped up to a higher ring or level that it could be in. So we could have what we call, a photon emission when I have that electron in this higher state. So this one here is going to hop down back to the ground state, the lower state here, and in doing so, it emits a photon. And that is sort of the discrete energy line that we see in the spectrum. We see only that specific color that corresponds to this photon here. Likewise, he figured that the reverse could happen. If I had my two electrons in the ground state and I shoot in a photon of just the right energy, I can actually hop that electron up, absorbing the photon. And just like with our photoelectric effect, that photon has the energy to shoot the electron from the ground state up to the higher one proportional to its frequency. So Bohr, he decided that these electrons, he used a very simple model to sort of figure out. He wanted to know, yeah, there's these levels here, but how far away are they from the nucleus? So he proposed this sort of simple model, just based off classical physics that we all know. He said the energy of the electron had to be its kinetic energy plus its potential energy. We know its kinetic energy is 1/2 mv squared, and the potential energy is the sort of attractive potential energy due to being in proximity to the nucleus. So we have this electric potential energy, kq squared over r, due to the attraction of the nucleus. So this is just our UE, electric potential energy. He also said that, the force, these electrons are going to move in a circle at these fixed levels, mv squared over r. And the only force that would be acting on the electron would be the electric force due to the proton. So what he was able to do was he was able to say that the velocity of the electron moving in this orbit should be kq squared r over m. Velocity squared, rather. If the electron were just a particle, we run into the problem that it would radiate like a classical charge, and it would lose energy and fall down into the nucleus. He proposed that electrons are standing waves. So here's our nucleus. The electron is sort of a standing wave with nodes and antinodes and all that good stuff. So we have this sort of wave-like orbit around the proton. And he can find that the wavelength of this particle had to be some integer multiple of the circumference of that circle. So he's looking for this radius here. He wanted to know how far away these things were. And what he eventually found was that r had to be some multiple of n squared from some base radius, which we now call the Bohr radius after Bohr himself. So sort of the average place that an electron could be in this model, at least, was, for each energy level n above that, we could square that and multiply it by some base value. What he found then was that the energies required to sort of move these electrons between the radii were that E was equal to negative 13.6 electron volts over n squared. So this number here, electron volts, is a unit of energy. It is the amount of energy that you get when an electron is accelerated by 1 volt, and therefore it's equal to 1.6 times 10 to the 19 joules. That's 1 electron volt. Here we have 13.6 electron volts. So what this formula tells us is that if I have an electron in the ground state, n equals 1, and I want to get it off of the get it off of the atom completely, then I need to put in 13.6 electron volts to do that. So negative, we'll say 13.6 electron volts is the ionization energy of the hydrogen atom. If I'm already in state 2, for example, I have n squared is 4, then it takes less energy to liberate that electron from the atom. So the larger the n value, the higher energy that I already have, the less energy is required to knock it away from the nucleus. This approximation, with the simplest model as he used and as incorrect as a model as he used, actually works really well. So the Bohr model works really well, but only for atoms with a single electron. So it works, or at least a single electron in the outermost orbital. So it works really well for hydrogen. It works really well for, lithium, which has 1 electron in its outermost orbital. But it doesn't work for helium. It doesn't work for a random transition metal. It works for sort of, one extra electron in the outermost orbital. And so it wouldn't be until, the 1920s and 30s when we really develop quantum mechanics and we have the Schrödinger wave model that we have our most up-to-date model of the hydrogen and other atoms as well. So the Schrödinger wave model predicts not electrons as standing waves, but as sort of clouds of probability. And we'll talk more about that when we get to quantum mechanics. But for now, note that the clouds of probability model is sort of the currently accepted model. So for all that Bohr did right, it still has a very good way of thinking about how atoms jump from level to level. So let's say we have a simple atom with only 3 states. So we have a ground state with n equals 1. We have a state n equals 2, and a final state n equals 3. So there were going to be certain energies associated with, this state. So we could call this, 0 electron volts. We could say to hop up to state 2, we could have, say, 2.2 electron volts. And then finally, from the ground state to state 3, we have a total of 3.1 electron volts. These numbers are all completely made up. This is a completely fictional atom, but it's the model and sort of the things I want you to see here that are important. So this atom has 3 states: ground state, n equals 2, n equals 3. If I have an atom in n equals 3, there are 2 possibilities. It could fall all the way down to the ground state, in which case we'd have E31, and that would be, a complete 3.1 electron volt difference. Or it could fall from n equals 3 to n equals 2, in which case we have the difference, 3.1 minus 2.2, we have 0.9 electron volts associated with that transition. Likewise, once that state is now in state 2, it can fall back down to n equals 1, and so there's another possible transition here where I have a delta E 2,1 that is equal to 2.2 electron volts. So the allowed sort of things in the spectrum, the allowed frequencies and wavelengths we can see in an atomic spectrum are dependent on the sort of spacings between these energy levels. A photon with energy 3.1 electron volts will have the corresponding frequency of that energy by HF. So we can calculate what wavelengths and frequencies will be in this spectrum by looking at the differences in energies between all possible states. All right, I've traveled on long enough. We'll stop here. Make sure to check out the checkpoint questions on the website so that you can sort of take attendance for the day, and have a great day.